Hello, this is Hannah Bond, and this is my webcast for week 12. As I've been reading, in Unit 4, I see that materials are going to be a major challenge for me on this unit on magnetism. My school, we don't have anything remotely similar to the powerful horseshoe magnet that you showed in your demo in class last week. And also, I don't have either a cathode ray tube or an oscilloscope. However, I'm not sure what I'm going to do in terms of this type of demonstration with this, powerful horseshoe magnet. I did read the instructions for constructing the current balance, and that seemed to be fairly straightforward and easy to understand. One challenge will be finding someone with a radial arm saw that I can use to cut through the 1/8" thick metal, but I don't think that should be insurmountable. So I expect that over the summer I will probably be able to construct this type of device. Some of the things as I've been reading for this week, in the pre-lab discussion for Lab 3, the teacher guide says, and here this is a quote, "Throughout the earlier unit, it was observed that the thing that creates a field responds to, experiences a force in, that same type of field." The labs that preceded this have established magnetic fields are created by moving charge. Lead students through the logical argument that moving charge must therefore experience a force when subjected to a magnetic field. And that's the end of that quote. The statement made me think, and I guess I had not observed this fact clearly in previous classes. Yes, I knew that a mass generates a gravitational field, and that another mass does experience a force in that field. And that is also true for charge. A source charge creates an electric field, and a test charge experiences a force in that electric field. So, I guess it was just seeing it in a different way made me really think about and appreciate that a little bit more. So, this week, I have done the reading for the magnetic discussion, but I've also been reflecting about how things have gone as I've tried to incorporate some of the things that we've been discussing in our electricity and magnetism class in my own classroom this spring. So first, I'll give just a quick summary, because I'm not going to be able to do the full modeling curriculum this spring due to time constraints. I am going to try to incorporate more of it next year in my classes. But here's a summary of what I have done. So I taught the full modeling sequence for Unit 1 on charge behavior and interactions. So that unit I did completely. And from Unit 2, I used the initial activity to define potential, and then I also used a PhET simulation to explore electric potential. But I primarily taught about potential in the more traditional manner guided by our textbook. And then for Unit 3, circuits, I discussed how charge distribution throughout the circuit creates the electric field that drives current through the circuit. But I did not do the first lab, called What's Happening in the Wires. My class began with Lab 2, concerning charge distribution and potential difference. My students used a voltmeter in the circuit, and they observed a large increase in electric potential across the battery, and then they saw very small potential drops through the wires, and a pretty large decrease in potential across the bulbs. I don't plan to have my students derive Ohm's law or the factors that affect resistance, and instead I've been covering those concepts just through lecture. My students will, though, perform a lab with series and parallel arrangements of light bulbs and resistors. And so they will derive the expressions for equivalent resistances for both the series and parallel wiring. And then they will demonstrate Kirchhoff's loop and junction rules, which demonstrate conservation of energy and conservation of charge. At that point, I also plan to use three-dimensional models of circuits to quickly explore a larger variety of circuits. So, going back and reflecting more on Unit 1, I was able to do everything in that unit and had pretty good success with it. I followed the complete sequence in the AMTA materials, and I started with a demonstration of rubbing a balloon and sticking it to the whiteboard, and had students create a force diagram. From that, they inferred that there was a new type of force that we hadn't discussed previously. They had enough prior knowledge to understand that the force had something to do with static electricity. Then we performed the sticky tape activity in teams of 3. The results were really good. I did modify the worksheet to improve the instructions, but overall that activity went better than I had really originally thought that it might. The students really seemed to pick up quickly on the diagrams that showed the effect of polarization at an atomic level. Then we also did the electrophorus activity as a whole class demonstration. My class is only 9 students, and so it was doable for us all to get around one table and do this together. And then we completed the worksheet on whiteboards. And that worked very well. Then I demonstrated the Van de Graaff generator, and we discussed the conductors and insulators worksheet as a class. For the Coulomb's Law lab, I used a gizmo from Explore Learning, which is shown here. I like this gizmo, and it's easy to use, and so I had students perform 3 experiments because there were 3 potential independent variables. There was the strength of each charge, charge A and charge B, and then they could also change the distance between them. So they did 3 experiments and graphed all of those relationships. The dependent variable, of course, was the force. And then after graphing those 3 relationships, they merged them to a single model to explain how the electrostatic force depends on the strengths of the 2 charges and the distance between them. After this lab, I introduced some other concepts like elementary charge, quantization of charge, conservation of charge, and so on. And then we worked on applying Coulomb's law in a number of types of quantitative problems, and also how to do superposition when the field has more than 2 charges. So then, moving on in Unit 1, my class did the activity to introduce the electric field, where each student calculated the electrostatic force of attraction between the charge at the center and whatever charge I assigned them in their assigned location, and we sketched the vectors on the whiteboard. We observed that the force vectors all pointed radially inward toward the source charge, and that the magnitude of the force vectors were greater when they were nearer the source charge. Also, at the same distance from the source charge, the force vectors were all the same. So we talked a lot about how the field exists in space due to the presence of a charged object, regardless of the presence of a test charge. So you could have a field even if you only have one charged object, but in order to have a force, it requires 2. This activity was really helpful in bringing out a lot of good information. The fact that the electric field is what mediates that electrostatic force, and how the amount of the force will be greater when the field lines are closer together. We talked about the convention that the electric field vector points in the direction that the force would act on a positive test charge. And that's the reason that we represent field lines always coming out of positive charges and always moving into negative charges. So, we talked about the analogy of the electric field to gravitational field. In gravitational field, we define the gravitational force as the field strength, G, small g, as the ratio of the gravitational force F on an object to the mass of the object. So the gravitational field strength equals the force divided by the mass. And so we took that analogy and extended it to electric fields. Said, okay, well, then the strength of the electric field E must be equal to the ratio of the electrostatic force to the test charge Q. So E equals FQ. We had a lot of discussion, and I'm not sure that I satisfactorily explained why we really need the concept of electric field. My students are much more comfortable with the concept of force, and but we talked about how that if you know the field at a location, you can very quickly find the force on any size charge that you might put at that location, and we'll also know the direction of that force. And then finally, we used the PhET and a modified version of worksheet 4A to explore electric field and do a little bit of that. And overall, I think that this unit went smoothly. I'm sure that I'll be able to improve on the experience next year when I go through this cycle again, and have a little bit more time to plan and create the worksheets and things like that. But I think that this was a nice improvement to my class in terms of a better, stronger understanding of electric field this year, and also much better understanding of the underlying reason for the electrostatic force and what's happening, and also why neutral objects are attracted by charged objects. That was a huge improvement over previous years. Okay, thank you.